Hello students, welcome back. Let us resume our discussion in section 2. Previously, we went through the interval estimation, and there we had two things to focus upon. Number one, the expected value. Just subtract one from the other and get the difference. Whether you use mu1 minus mu2 or p1 minus p2 or pi1 minus pi2, it doesn't matter which character you use. Just subtract one from the other and that's it. Now, the standard error, on the other hand, is not that simple. Here's the formula. Now, how do you get that? Well, it comes from the Pythagorean identity, which actually comes from some kind of geometrical understanding in multivariable calculus. And then apply the SE formula for proportion for the first and the second samples, and we get this kind of derivation. Eventually leads to this. If you follow all those, great. That way you can organize all these ideas a little bit better, more systematic, so that you can go over to deep understanding and of course more solid understanding as well. But if you can't follow, then just record this formula somewhere and utilize it whenever it becomes necessary. And this formula is for interval estimation. Now let's go to hypothesis testing, and there we're going to end up with a little bit different standard error formula, even though deep down they all go back to this Pythagorean. Okay, let's begin. Hypothesis testing. We have either these kind of structure or those kind. They're actually equivalent. We have two samples, so one sample has proportion pi1 and the other sample has proportion pi2. And the idea here is null hypothesis means no difference. So pi1 and pi2 must be equal, or at least approximately equal. The alternative, of course, is one greater than the other, or simply they're different. Either pi1 is greater, or pi2 is greater, or they're just different. Those are going to be the alternative hypotheses. Now, what if we subtract one from the other and get pi delta, which is pi1 minus pi2? In that case, you're going to get these. You can compare those with 0. And this form, after subtracting and then comparing with 0, will be a little bit more convenient in terms of graphics. Because you're going to draw the graph, the normal graph, centered at 0. As for finding out the standard error, however, this form will be a little bit more convenient. Now, speaking of standard error, here's the standard error formula. Square root of p1 minus p times 1 over n1 plus 1 over n2. We're going to talk about this part a little bit later, 1 over n1 plus 1 over a2. As for this part, I hope everybody remembers, this is the variance for Bernoulli random variable. And then if you repeat all those and apply central limit theorem and so on, then you get square root of p1 minus p over n. And here we have two samples, so we have a little bit different, but added. But then again, what is this p? It turns out that p comes from this. So we have to somehow reconcile pi1 and pi2, which may be a little bit different, because under the null hypothesis, pi1 and pi2 must be approximately equal. So somehow I have to reconcile them. How do I do that? For some strange reason, we do this. Add of the numerator, and then add of the denominator, and then form this fraction. Does it make sense? Probably not. So let's get these through an example problem. Hopefully you're going to understand this a little bit better with an example problem. Okay, here we go. A salesperson for a new manufacturer of cell phones claims not only that they cost the retailer less, but also that the percentage of defective cellular phones found among their products will be no higher than the percentage of the defective found in a competitor's line. To test this statement, you do some sample studying and you got this result. Now you want to test it. All right, let's set up the problem. First, set up the hypotheses. So hypotheses, well, that's not too bad. Null hypothesis and alternative hypothesis. Now, null hypothesis typically means the proportions are the same, no difference. In this particular case, that means the defective proportion are same. Look at the sample. They look very different. 15 out of 150, that's 10%. 6 out of 150, that's 6 out of 150, that's what is 6 out of 150? Oh, 0.04, so 4%. So 10% versus 4%. Looks a lot, but, well, sample sizes are relatively small, so it's going to be coming from the randomness. And in reality, the difference must be the same. At least that is what the salesperson is trying to push you. The alternative hypothesis, of course, is the salesperson's defective rate is higher, as you can see from this sample study, more or less. So let's write like this. Pi 1 is significantly greater than pi 2. Okay, all right. And then let's go ahead with some sample statistics. Sample size N1 is 150. Yes, 150 checked. Sample size N2 is also 150. Again, they checked 150. These numbers in general do not have to be the same. In this particular case, they're the same so that we have a little bit easier computation. But if they checked 160 phones of the salespersons and then checked only 90 phones for competitors, well, that can happen. So you use 160 and 90 for N1 and N2. Now proportion, first proportion, defective proportion, 15 out of 150. And that's 10%, isn't it? Competitors' proportion of defective phones, 6 out of 150, and that is approximately equal to 0.04, 4%. Okay, from here we can calculate the standard error. N1 and N2, we know those, 150. As for p-value, you have to do this. Add up the numerators and add up the denominators. So here we go. P is add up the numerators and add up the denominators. And eventually what you get? 21 over 300. And that's approximately equal to what? Let's do this computation. Okay, 0.07, 7%. And how am I doing, or why am I doing it this way? Well, null hypothesis is claiming there's no difference. So first sample coming from the salesperson's company, and the second sample coming from the competitor's sample, they're the same characteristic according to the null hypothesis. So put all those together and consider a big sample of 300 phones now, and then count the total number of defective. That's how you can reconcile pi 1 and pi 2. That's how you do that. Does it make sense? Now, if you want to compare the difference, you see, pi delta or the sample static will be p delta, then that's going to be the difference between these two. P delta, delta is for difference. Oh, 0.06. Okay, 10% minus 4%, so the difference is 6%. And then, as for the reconciliation of this P1 and P2, we do this. Add up the numerator and then add up the denominator and get a new proportion. The idea behind it, under the null hypothesis, yes, we are looking for basically the type 1 error. So under the assumption the null is right, we draw the normal curve and do everything. So based upon that, there's no difference between these two samples, salesperson sample and competitor samples. So put all those together and we get a total of n1 plus n2. And then among those, number of defectives, x1 plus x2. In this case, total 21 defective out of total 300 selected and tested. And that'll turn out to be 7%. Therefore, we can do this SE computation. And that's approximately equal to, let's see, P is 0.07, right? 7%, 1 minus of that. And then 1 over 150 and 1 over 150. Calculating all those, let's see, what is this quantity? Okay, there you go. That is your standard error for the problem. So this completes the setup. The hypothesis, the null and alternative hypotheses, and required sample statistics are here. The sample size and proportions, and then the difference of the proportion. This one, which I'm highlighting in green. Now, that's not all. Even though I have this P1 and P2, instead of using this formula here, as we did for interval estimation, we do something different. Under the null hypothesis, P1 and P2 are just observed values coming from the same parameter, pi 1 and pi 2. So you have to somehow put those together and reconcile those. How do we do that? Under the assumption of the null hypothesis, sample 1 and sample 2 should have no difference. So you can put all together and make one big sample and get the proportion. That's how you get this P. And that's why you're adding up the numerator and adding up the denominator. Once you do that, then you can put all those into the SC formula, and we got it. And that completes the setup. Now, how do we test those? Using either critical value approach or probability value approach? Well, we're going to do those in the next video.